Okay, so let's start. Welcome to week nine's problem solving session. So we'll solve the problems related to week nine's assignment, and then we'll solve this year's week eight assignment. Let's quickly recap what we did in this week. So in this week, we saw the proof of the theorem, the following theorem, that parity is not an AC0 due to Haas-Star. Now, recall it in the last class, we had seen that parity not in AC03. So we had seen a stronger result in last class, but we are seeing this result in this class because the proof techniques are completely different. So the mm, proof that we saw in last class used the polynomial method, and this is using random restrictions. And so the one of the crucial part of this proof is Hastad switching lemma, which says that if f is a KDNF or a KCNF, and rho is a random restriction that leaves Pn variables untouched, then probability over random choice of rho, so that F restricted to rho is not an SDNF or S. Oh wait, this should be CNF DNF because this is DNF CNF. Yeah. So if F is a KDNF, then the probability that F is not a SCNF, and if F is a CNF, then the probability that it's not an SPNF is at most C times P times K to the S for some constant C. Okay. And the way we proved the theorem using this lemma is as follows. So we start off with a depth delta circuit and we repeatedly apply the switching lemma to it to reduce its depth. And one application of the switching lemma reduces depth by one. Okay. And finally, we have a CNF or a DNF which cannot compute parity on the remaining variables. Sorry, which computes parity on the remaining variables, but we know that the CNF or a DNF needs to be large to compute parity on the remaining variables. So if the starting circuit was small, this CNF or DNF would this CNF or DNF would be small, and so that CNF or DNF won't be able to compute parity, and so the entire circuit can't compute parity. So this is a very high level outline of the proof. So if you have any questions about the switching lemma or the proof of the theorem, you can ask now. Otherwise, we can start with the problems. Okay, so I think we can start with the problems. Oh, but just give me one second. Okay, sorry for that. Okay, so the first problem is this. Yeah. into an equivalent formula. Of size s to the order d, and yeah, a C can have gates with unbounded value. Okay, so to prove theorem one, we took any AC0 circuit and converted it into a very special form, right? So the special form was that it was a formula with alternating layers of and OR gates, and all the NOT gates were at the bottom, right? So what we are going to show here is in the first few questions is that we can do this conversion. Okay, and the first step of the conversion is to convert size S step T form circuit with gates having unbounded fan-in to size S reorder D depth D circuit. Now, suppose S is poly n, where n is the number of inputs, then S to the order D is also poly n because D is constant, right? And so this blow up in size is large, but it's fine as long as D is constant because we are only looking at SE0 circuits, right? So let's see how to do this. Okay, so what's the difference between a circuit and a formula? Okay, so in a circuit, every gate can be an out. So the output of one gate can feed into multiple gates. However, in a formula, the output of every gate must feed into exactly one gate, right? So to one way to convert a circuit into a formula is to pick any gate, see how many gates it feeds into, and then replicate the gate that many times. Okay, and that's exactly what we are going to do. So what we'll do is the following. So we don't need to worry about the output gate. The output gate, I mean, its output does not feed into any gate, so we don't need to worry about replicating that. So let me define this. So okay, uh, we don't- okay, actually it's fine. I can do it without. Okay, so what we are going to do is okay, let me call the gate H. The circuit obtained. Okay, so let's see what we are doing to obtain D. So what we are doing is we are okay. So what we are doing is we are taking every gate in C, replicating it as many times as there are paths from that gate to the output gate. Okay. Now I okay and okay. I also need to tell you how we are connecting the graphs, right? Then yeah. So we are replicating it these many times. Now uh, let's see why this helps. So take any gate and look at the number of paths from it to the output gate, right? My claim is the number of times that gate is being used is that number. So is the claim clear?
Yeah.
Yeah. And the reason is the following. So let's say you look at the gates directly connected to the output gate, right? Those you only need to replicate as many times as they feed into the output gate. So for example, let's say one gate feeds into the output gate twice. We need to replicate it twice. Okay. But now look at some gate that feeds into this gate, right? Let's say it feeds twice. So that now we need to replicate it four times. Why? Because one for the first replication of the output gate and this other for the other ones. Let's say this is the output gate. There is one gate that feeds twice into the output gate. Then there is another gate that feeds twice into it, right? So to get a formula, you need you need to replicate this gate twice and this gate four times, right? So that's the number of paths from this gate to the output gate. Okay, yeah, and okay, so once we have replicated this, what we'll do is yeah. So uh, yeah, so this is how we have constructed D. Now, so is the construction of D fine? So if the construction of D is fine, then so first observe that yeah, I mean that's this is pretty straightforward. Then yeah, and D is a formula because whenever we need whenever a gate was used twice, we were using a different copy of it, right? So give me a second. Yeah, sorry. So D is a formula. So in the question we had to come up with an equivalent formula for C. So D is an equivalent formula. Now let's look at its size and its depth. Okay. So again, the depth doesn't change, right? Because when we replicate gate, it's still the same depth. So depth of uh, and size. Okay. So okay, for to count the size of D, one thing we can do is the following. We can just count the okay. So we'll count the number of gates in D. Sorry, yeah, we'll count the number of gates in D. And now observe that every gate uh, is the output of every gate feeds into just one gate, right? So with every gate, you can associate its out the edge that corresponds to its output, right? And what that will tell you is that the number of edges in the graph, sorry, the number of edges in the circuit is at most twice the number of gates. And so to calculate size equals to number of edges, all you need to do is find out how many gates are there, right? So size of D is at most two times the number of yeah, Okay, so now let's count the number of gates in the circuit, right? So let see define the depth of G as uh, G to the output gate. Then the number of paths from G to the output gate is at most S times the depth of G. Why? Because so we know that the size of C is at most is S. So okay, so how many gates can G be directly connected to? So look at any uh, ah, so look at any path from G to the output gate, and let's say the nodes on that path are V1, V2, V3, and so on, right? V1 is the one directly connected to G. So ga- how many possibilities are there for V1? S. How many possibilities are there for V2? S, and so on, all the way up to V depth G, right? So the number of paths is at most S times S to the depth G, and so in D, G is replicated less than equals to S times depth of G many times. Okay, and so now depth of G is less than equals to D. So uh, number of gates in D is S for like different possibilities of G, and for each G it's S to the D, right? So this is like yeah, so this is the number of gates in it, and so the number of edges is two times this, which is also S to D order D, right? So the number of so the size is also S times order D, and so all four conditions are satisfied. It's an equivalent circuit. It's a formula. Depth is D and size is S to order D. So is this fine?
Yeah,
Yeah. Uh, okay. So now let's look at the next problem. Yeah. I'll be back in a minute. Ah, Okay, yeah. So let's get the next problem. Yeah. Okay. So we have converted a circuit to a formula. Now we want to convert that formula into a formula with alternating layers of and an OR gates and with all the NOT gates at the bottom, right? So let see. Unbounded formula. The size of the new circuit should be less than equals to S, and depth is less than equals to D plus. Yeah. Okay, so we need to, so we, whenever we have a NOT gate, we want to sort of push it down, right? So suppose that we have a gate like this. So suppose that somewhere in C, we have a NOT gate which is connected to the output of an OR gate, and OR gate's inputs are F1 to Fn. Okay. Now my ultimate goal is to push this NOT gate all the way to the bottom, right? So what's the first step in this process? The first step in this process would be to sort of switch the places of OR gate and NOT gate, right? So now the OR gate the output of the OR gate is connected to the NOT gate. So the OR gate feeds into the NOT gate. Now what I want to do is the other way around, right? I want to feed, I want the NOT gate to feed into this OR gate, right? So how can we do that? Okay, so one way is using just De Morgan's laws. So this is not F1 and M, De Morgan's law. And similarly, again, De Morgan's law. Okay, so what the first thing does is it converts something like this into something like, oh, sorry. The first converts something like this into something like this. So it pushes the NOT gate down by one, and the second one converts this to this. So it also pushes NOT gate down by like by one, right? And we do this repeatedly. Uh, okay, I think I should write S plus N over here. Yeah. Okay. Yes. So this is what we are doing. And now after this process is complete, now all gates, okay, let the new circuit be D. So note that it's still a formula, right? Because what's happening is, let's say, pick any gate. If pick any AND or OR gate. If earlier its input was feeding into a NOR gate, now it's feeding into some other AND or NOT gate, right? So while the gate it's feeding into changes, the fan out doesn't change. So D is still a formula. Uh, all NOT gates are directly connected to the inputs. Uh, yes, okay, so yeah, and D computes the same function, yeah. So, so D is an equivalent formula which computes the same function. It's an equivalent formula and all the NOT gates are at the bottom, right? So now we need to look at the size and the depth of D. So, okay, so the number of, okay, my claim is that the number of AND and OR gates are the same in C and D. Why? Because the only thing that's changing is that the number of NOT gates, right? What's happening is that an OR gate is becoming an AND gate and AND gate is becoming an OR gate, but yeah, the total number of AND and OR gates is going to remain the same. And so the number of, and this is at most N. Why? Because the number of all NOT gates in D are at the bottommost level. They are directly connected to the input, and there are at most N inputs, right? So the number of gates is the number of NOT gates is N. And okay, yeah, let me just write order Sn because yeah, yes, the number of gates in D is S plus N. So yeah, the size of D is two times this. So like order S plus N. And let's look at the depth of D. Okay, so what okay, what is happening is that now you have these NOT gates at the bottommost level, right? So that's the only increase in the depth. So depth of D is D plus 1. So D levels of AND and OR gates, the same as C, and then one potentially one additional level of NOT gates. So size is order S plus N, depth is D plus 1, all gates, NOT gates are at the bottom, D is a formula, come to the same function, so it satisfies all the condition in the question. So is this fine?
Yeah.
Okay. Okay, so now we have pushed all the NOT gates to the bottommost level. Now what we want to do is we want to ensure that the AND and OR gates are alternating, right? So let's see. S and with all NOT gates directly connected to the input. Convert yeah, and this transformation is very simple. So what do we want to do? We want to have alternating levels of AND and OR gates. So let's say we have an AND gate. Okay, first of all, this is the formula. So every gate is going to feed into just one other gate, right? So let's say you have an AND gate which feeds into an AND gate. Then you don't want this structure, and you also don't want a structure where an OR gate feeds into an OR gate, right? But this is simple because you can just collapse the AND gate and the OR gate, right? So and AND gate, another AND gate. So we just collapse the gates. Okay, correct my charger. Yes. So what I mean is this. So let's say you have something like this, and other inputs. Then what you do is, okay, this, okay, let me name the inputs. Let's say this is F1, this is F2, and Fm, and let's say this is G1 to Gm. Then what you do is one AND gate and C for all. Yeah, and so now after you've done this, every AND gate feeds into an OR gate, every OR gate feeds into an AND gate. So you have alternating levels, right? Okay, so this is still a formula. Okay, let the new circuit be T. So D is a formula and computer is still a formula. Yeah, so D is a formula equivalent to C. Now we need to look at the size and the depth of T, right? So size is why? Because all we are doing is collapsing gates, right? So the number of gates can't go up; it can only go down. And we know that yeah, there is a okay. Let me just write order S because yeah. So the number of gates can't go up; it can only go down. So the number of gates is still order is S, and so the size is order S, like 2S at most, and the depth is less than equals to D because again, when we are collapsing gates, the depth doesn't increase, right? So it's an equivalent formula with size order S, depth D. So this is all we need. Is this fine? Yeah. Yeah. Uh, uh, Premium. Yes, now let's look at the next problem. Yes, the next problem is the following. Yeah, so the main result so that we saw this week was that parity is not in AC0. Uh, what we'll now see is that using parity not in AC0 can also show that majority is not in AC0. Okay, so okay, so we want to prove that majority not in AC0, and we already know that parity is not in AC0. So one natural way to do this is the following: is to show that suppose major it's by contradiction. So suppose majority was in AC0, then from the circuit for majority, from the AC0 circuit for majority, we can construct an AC0 circuit for parity. Okay. But now we know that there is no AC0 circuit for parity. So our assumption that there is exists an AC0 circuit for majority has to be false, right? And so majority is not an AC0. So this is exactly what we'll do. So the idea is uh, yeah. So this is the idea. So now let's see how we'll construct this circuit. So that is CM computes the majority on M bits. Uh, consider the Yeah, so T n x is or over I from 0 to floor n over 2 minus 1, uh, not C 2I x concatenated with, okay, 0, no, 0 to the 2I plus 2, 1 to the n minus 2I minus 2, and C2n of x concatenated with something wrong. I am for a 0. Okay, what do I do here? For all zeros, I want here n plus 1 many ones. For 0 I zeros, I think this should be over here. Yeah, yeah, because so this would become majority when it's 2I plus 1. Yeah, so 2n, uh, 2I plus 1, 1n minus. Okay, so this is how we are going to construct the circuit. So the circuit is just, okay, so to construct DN, what we are doing is, so DN is an n input circuit, right? To construct DN, we are using 2n input circuits from the circuit family CN. So we are using CN, C2n, and DN is all of a bunch of these things, and every one of these, okay, so here it's C2n, and our X is just n bits long, right? So we need to make it 2n bits long, and the way we do it is by concatenating this string with X. Okay, so is the construction fine? Okay, so if the construction is okay, then okay, I'll show you why this computes majority. Sorry, why this computes parity. But first, let's look at the size and the depth of DN. So this OR gates adds at most n over too many edges plus this NOR gate. Yes, so this NOT gate adds at most one edge, and this AND gate adds at most two edges, right? So it's 3 times n over. Okay, let me do it stepwise. Otherwise, it's going to be messy. Okay, so the size of each C2n. So this is okay. So C2n is an AC0 circuit. So the size of this is poly 2n, which is poly n, right? Now D has, okay. How many C2ns does D have? So per bracket, it has two of C2ns, and there are at most n over two brackets, right? So it is at most two times n over too many copies of C2n. and size of these copies is so each and every is poly n, so it's n times poly n, which is still poly n. Okay, let me keep it n times poly. I'll just simplify everything later. Okay, now per bracket, it D has one AND gate and one NOT gate. So this is three edges. So and at most n over two brackets. So these contribute like 3 times n over 2 to the size. And again, it has like OR gate has at most like n over 2 edges. So the total size is n over 2 plus 3n over 2 plus n times poly n, and this is just poly n. Yeah, so the size is poly n. Now we need to show that the depth is constant. So the depth of D is just the depth of C plus C. These three gates are added, right? So it's the depth of C plus 3. So it's D and not D. Yeah, because C2N is an AC0 circuit. So D itself is an AC0 circuit. Now all we need to show is that D computes parity, right? So is it fine that D is an AC0 circuit?
Yeah,
Yeah. Then let's just show that it computes parity. Give me a second. Yeah. So let's look at this proof. So, okay, so parity and okay. So parity, recall that parity is one if and only if the number of ones in X is odd, right? In other words, it is one if and only if in X is exactly equals to 2i plus 1, right? So this goes from 2i plus 1 goes from I to at most n, right? So I can write this as the number of ones in X is at most 2i plus 1 and number of ones in X is at least 2i plus 1. Okay, so so we have an expression for parity in terms of these two inequalities, but we now want to somehow compute these two inequalities using majority. And this is sort of like computing the threshold function using majority, which we saw in one of the lectures we can do. And this is something similar. Okay. So now, okay, suppose that the number of x, ones in x is at most 2i plus 1, right? In that case, my claim is this, that this is the same as Q1, 2, and okay, so my claim is that these two are exactly the same. Let's see, 5. So suppose that x has at most 2i plus 1 many ones, right? Now, how many ones I'm adding over here? I'm adding n times 2i minus 2 many ones. So now the number of ones in x is n minus 1, right? And because of this, this is 0, right? So why? Because the number of ones is n minus 1 and the total number of elements is 2n. So if number of ones is at most 2i plus 1, then this majority is 0. Now let's look at the other direction. Suppose this majority is 0, then the number of ones in x, okay, then the number of ones in this string is at most n minus 1. So the number of ones in x is at most minus n minus 1, which is equal to n and get cancelled out, 2i, oh, sorry, the number of ones in x is at most n minus 2i minus 2, and it get cancelled out. This is 2i plus 1, right? Yeah, so When this is 0, the number of ones in X is at most 2I plus 1. And so this is the first part. So is the first part okay?
Yeah.
Yeah. Can you do this later? Minus 2I minus 1. Okay, now I should change this over here. 2I plus 2I plus 2 and rest of this one. Yeah. And this is the same. Yes. Okay, so now the second claim is that this majority is 1 if and only if the number of ones is at least 2I plus 1. Again, let's see both the directions. So if the number of ones is at least 2I plus 1, then adding 2I plus 1 over here would give me at least n ones. And so this majority is 1, right? Similarly, if this majority is 1, then x must have at least, sorry, this entire string must have at least n many ones. And so x must have at least these many ones. So this is also true. So again, both sides are fine, right? And so this I can further write as, yeah, so if this equals to 0, then not of majority is 1, and the second one remains as it is. And now since D2n, sorry, C2n is the circuit for majority, I can write this as, and this is just Dn. And this proves it. So is this fine?
Yeah.
Yeah. Okay, so then before we look at the next problem, just give me a second. Okay, so let's look at the first problem. So prove that uh, TC0 is not contained in AC0. So recall that TC0 is a circuit with unbounded fan and threshold gates of constant depth and Pauli size. Now, we saw, okay, so parity is clearly in NC1. So parity not in AC0 immediately shows that NC1 is not contained in AC0. But what we know is this, right? So there is AC0, there is TC0, and there is NC1. Now, parity not in TC0 parity not in AC0 shows us that these two are different. And now we want to show that something stronger is true that these two are different. Okay. And okay, so the way we do this is simple. We'll use the previous problem. So the previous problem we showed that majority is not in AC0, right? We'll show that majority is in TC0. So now we have a function which is in TC0 but not in AC0. Uh, so TC0 cannot be contained in AC0, right? Okay. A better way to write it would be this. Prove that AC0 is strictly contained in TC0. That would make like that diagram much more meaningful. Yeah. Okay. And we'll show that. Okay. So how can okay? So here's one very straightforward way to construct uh, TC0 circuit for majority. So can you suggest a TC0 circuit for majority? It's going to be just one threshold gate. All you need to tell me is so over here it would look like A1 X1. 1 or 0 otherwise. So you just need to tell me what A1 to A and theta are. So like, can you come up with A1 to A and theta so that this would take a majority? Okay, so here's one way to do it. So yeah, A1 to A and R1 and theta is N over 2. And the size is just 1. So size is 1, depth is also. Yeah, so majority is in TC0, but not in AC0, and so AC0 is strictly contained in TC0. Is this fine?
Yeah.
Yeah. So then let's look at week 8's assignment. So the first problem is which of the following is false? Uh, Mod 2 is contained in ACC04. Mod 2 is not contained in ACC03. Mod 9 is contained in ACC02. And mod 5 is not contained in ACC07. So which of these is false? Okay, so it's C. Yeah. Okay, so what we'll do is we'll show that A, B, and D are true, and also that C is false. Okay. Okay. So in an ACC04 circuit, we'll have mod 4 gates, and using that we want to simulate a mod 2 gate, right? So now a number A is, the way we do it is the following. So number A is 0 mod 2 if and only if 2 times A is equal to 0 mod 4. Why? Because let's say uh, A is 0 mod 2, which means A is 2 to the m for some m, and which means 2A is 4m, and which means 2A is 0 mod 4. And similarly, if 2A is 0 mod 4 and 2A is equal to 4L for some L, so A is equal to 2L, and so A equals to 0 mod 2. So all we need to do now is, okay, so a circuit for a mod 2 would look like this. It would be a mod 4 gate, but now the input would be multiplied by 2. Okay, so yeah. So I'm adding a 0 because multiplying by 2 is just equal to shifting, right? And when you shift, you get an extra 0. So is this fine?
Yeah.
Yeah. Let's see why B is true. Okay, so mod 2 is not in ACC03. So this is just from Rasmussen-Smolensky theorem because 2 and 3 are prime and they are not the same, right? So now let's see why C is false. Okay, before that, let's see why D is true. The reason is the same. Yeah, so in D we have mod 5 and ACC07. So 5 and 7 are distinct primes. And so the result follows from Rasmussen-Smolensky theorem. Same. So now let's see why C is false. Okay, so C says that mod 9 is an ACC02. So if this is false, then what should be true is mod 9 is not an ACC02. We would want to use Rasmussen-Smolensky theorem. However, in that theorem only works when P and Q are both primes, right? Over here, however, 9 is not a prime. So how can we show this? Well, one way to do it is the following. It's sort of combining Rasmussen-Smolensky theorem with what we did in A. So in A, we saw that uh, mod 2 is an AC04, right? So if I give you a mod 4 gate, you can simulate a mod 2 gate. What we'll do in D is the following. We'll show that if I give you a circuit for mod 9, then you can come up with a circuit for mod 3, but we know that you shouldn't get an AC0 circuit for mod 3, right? And this will prove that mod 9 kind of a circuit. So, Yeah, and the observation is similar. So if A is 0 mod 3, if and only if A is 3A is 0 mod 9. The proof is also same because and 3 is 0 mod 9. Yeah. So suppose C were uh, uh, C n plus 1 n plus 1 n bit defined as n plus 1 uh, x concatenated with 0. Okay, I don't need C. Maybe I think I just need uh, no, no, no. Okay, I don't think I need C n plus 1. So what do I need to do? I need to multiply this by 3. And so what will the input be? The input will be, uh, yeah, I don't think I need C yet. So I want to feed it 3 times x1 to xn. So this would be Cn plus 1 x1 to xn. And concatenated with 0 plus. And the reason for this is the following. It's okay. I need to write a 0. And the reason for this is this, right? So uh, x1 to xn multiplied by 3 is x1 to xn. Yeah. So this is 3 times x. And now this thing is has a circuit of size poly n, and like you're using your standard Luca and carry propagator or whatever. Okay. So is a circuit for, yeah, yeah. So this, the size is like size plus size of this plus size of this, which is poly n plus poly n poly n, and the depth is like order 1 plus order 1 order 1. So this is also an AC0 circuit for mod 3. So is this fine? Yes. Yeah, this is fine with this problem. So the next is pick the largest lower bound on the size of a depth T ACC03 circuit computing parity on n bits. And the options are 2 to the omega n to the 1 over d square, 2 to the omega n to the 1 over 3d, 2 to the omega n over 1 to 2d, and 2 to the omega n over n, 2 to the omega n to the 3 over d. So which of these is correct?
C.
Yeah, it's C. Okay, so the next problem is for an arbitrary input distribution from 0, comma 1 to the n, and given epsilon greater than 0, what is the lowest degree for which there exists a polynomial px over f3 with probability at most epsilon? The options are order 1, order log 1 over epsilon, order log 1 over epsilon squared, and order 1 over epsilon. So which of these is correct? Okay. So it's order 1 over epsilon, I think. Yeah, but let's work it out. So, uh, so let S1 to S T be random subsets of uh, n, and so the polynomial p that we used in class was this, right? 1 minus product I in T, 1 minus sum over J in S I x J squared. Yeah. Uh, so we saw in class that error for P is 2 to the minus T, right? And degree of T is 2 times T, right? So error for P is 2 to the minus T, so is at most 2 to the minus T. So it disagrees with or at most these many places. So this is what we need to equate with epsilon, right? Therefore, minus t taking logs equals to log epsilon implies t is equal to minus log epsilon implies t is equal to log. So minus log epsilon is log epsilon to the minus 1, and this is, oh, I can just write equals to. Yeah, so it's b. Is this fine?
Yeah.
Yeah. Okay, so now let's look at the next problem. So the next problem is this. Right, oh yeah. Suppose f from 0, comma 1 to the end to 0, comma 1 can be computed by a depth 4 ACC03 circuit with size n cube. Out of the following, select the smallest upper bound on the minimum error probability, minimum over p, probability x, px not equals to fx, as p varies over all polynomials in f3, x1, x2 up to xn of degree at most 8 log n over 4. The options are 1 over n, 1 over 4, 0, and 1 over 16. So which of these is correct? Okay, it's A, and the reason is the following. So the P constructed in class, the one we saw above, uh, error is at most S times 2 to the minus T for the entire circuit, because if the circuit has size S, and degree is 2T to the T where D is the depth. Yeah. Okay, so over here depth is 3. So over here degree is 2T cube. Oh, yeah, 2T, 2T to the 4, and S is n cube, right? So what do we want? We want the variable polynomials. Okay, so degree is at most this, and what's the error? So degree is 2T to the D is equal to 8 log n to the 4. Now D is 4, so 2T to the 4. So 2T is equal to 8 log n, and so T is equal to 4 log n. Yeah, and so T is equal to 4 log n, and now I want to find the error, right? So is at most S times 2 to the minus T. Now S in this case is n cube. Yeah, 2 to the minus 4 log n. So this is n cube over 2 to the 4 log n. This is n cube over, so I can take the 4 inside log and make it the power of n. So 2 to the log anything is that number. Yeah, so it's 1 over n. Is this fine? Because this is, and then let's look at the next problem. So the next problem is, suppose a probabilistic polynomial P for odd is constructed by picking L independent random subsets. Take the lowest upper bound on the error probability for any input, 1 over 2, 1 over 2 to the 2 to the L, 1 over 2 to the L, and 1 over L. So which of these is correct? Again, we can use the polynomial p over here. Yeah, so as we saw in third problem, it's this. Okay, so the next one is when transforming an ACC03 circuit into a polynomial, which gates possibly introduce error or mod 3 or and mod 3 and not and or. So which of these is correct? Yeah, so like it's or because as we saw, like the polynomial that we constructed for or has an error. For a mod 3, you can just replace it by a mod 3 gate, which you have in AC03 circuits. And for a NOT gate, it's like 1 minus the polynomial input. So not and mod 3 can compute exactly, but or can only compute approximately. So it's or that causes an issue. Okay, so give me a second. Okay, yeah. So the next problem is let P be a polynomial over F3, which agrees with parity on all inputs in the subset A subset of minus 1 comma 1 to the n. Let D be the degree of P. Pick the smallest k below such that all functions from A to F3 can be computed by polynomials of degree at most k. Okay, the options are n, d over 2, n plus d over 2, and n over 2. So which of these is correct? Okay, it's n d over 2. Well, let's see. Fine. So P agrees with parity on everything in minus 1 comma 1 to the n. So P is product I in n x I. So d, which is the degree of p, is n. Okay. Now any polynomial, sorry, any function from A, which is a subset of minus 1 comma 1 to the n. Yeah, give me a second. Okay, yeah. So Yeah, so n plus d over 2 is correct. Now let's look at the last problem. The last problem is how many n-variate multilinear polynomials of degree uh, at most d are there over the field FQ? Okay, q to the d, q to the n to the sum I in 0 to d, q choose I, and q to the sum I in 0 to d, n choose I. So any multilinear poly of degree less than equals to d can be constructed by picking coefficients for all monomials degree less than equals to d. So if the number of such monomials is m, uh, then the number of polynomials would be q to the n. So all we need to do is find m. Okay, so m. Okay, so in a multilinear polynomial, any monomial of degree I is just a product of I many different variables, right? So all you need to do to pick this monomial is to pick a subset of size exactly I of n. So this is n choose I, and so number of polynomials is q to the sum over I in 0 to d, n choose I. Yeah, so it's t. So is this fine? Okay, yeah. So if this is fine, this was the last question. So if you, unless you have any questions, we can end for today. Okay, yeah. So we can meet next time.